After our discussion in the Why Active CTLE video, lots of people asked how the detailed circuit implementation of the active CTLEs are, which we did not cover last time. Unlike the passive CTLE, there are lots of options to implement the active CTLE, and we'll discuss all possibilities one by one. Let's start with the most two popular CTLEs, which are Shunt-peaking type and source degenerated type CTLE, and you will understand why people prefer them a lot. For the active CTLE and the receiver X front end, we will use the Common Logic CML amplifier. First of all, we know the gain of the amplifier is Gm times R, which is the transconductance of the differential pair transistors times the output load resistance. But what I mentioned was the DC gain, or we think it's 3 dB bandwidth gain. Assuming the Gm value was the flat transconductance within the 3 dB bandwidth. From Microelectronics 101, you know the frequency response of the voltage gain will be a low pass response dominated by the output RC time constant. How do we implement the frequency dependent gain in a high pass instead of a low pass response? Since the frequency dependent impedance will produce the frequency dependent gain, we can simply apply the frequency dependent load instead of the resistive load. Think about which passive component's image is such that it can provide a high impedance at a high frequency, but low impedance at a low frequency for 5 seconds. Bingo! The inductor provides a high impedance at a high frequency and low impedance at a low frequency. Therefore, the high pass response of the gain is achieved easy, but obviously you might need 2 inductors in one stage and multiply by how many stage CTLE you need, which is the most expensive in the chip area, and change the signal routing for high signal bandwidth in design. The last critical change is the CTLE's tunability to accommodate different channel profile in any link. As we discussed in the passive CTLE video, the inductor was difficult to vary the inductance, so we can not only apply the inductive load to implement the CTLE's AC response, even though the shunt-peaking CTLE can also broaden the bandwidth between stages. A standalone shunt-peaking CTLE is not quite practical if the frequency-dependent load does not work well. Can we try to implement the high-pass response transconductance? Think about the source degeneration image of a common source amplifier for 5 seconds. Right, we can review the image of the single-ended common source amplifier without and with a source degenerated resistor as the starting point. A simple common source amplifier shows the source of the transistor M1 connects to the ground directly, and the transconductance Gm from the output current IR to the input voltage Vin will be the same as the transconductance Gm1 of the transistor. On the other hand, if the common source amplifier with a source degenerated resistor shows the source of the transistor M1 connected to the RS, then the output DC current IR will be reduced to a factor of 1 plus Gm times RS and the same input voltage Vin of the common source amplifier without source degenerated resistor. So the Gm of the source degenerated common source amplifier will be Gm divided by 1 plus Gm times RS. After reviewing the Gm of both common source amplifier without and with a source degenerated resistor, how do we map both GM or gain of a high pass response? Think about the gain images at the DC and high pass frequency for 5 seconds. Bingo! We want a smaller GM at the low frequency, which is exactly the common source amplifier with the source degeneration. We also want the greater GM at a high frequency, which is exactly the common source amplifier without source degeneration. Think about which passive component's image is such that it not only provides the short source of the M1 to ground at a high frequency, but also can leave the source of M1 connected to IS at a low frequency for 5 seconds. Right, a shunt capacitor in pair with the source degeneration resistor IS can provide such magic high-pass mapping for source degeneration at low frequencies and no-source degeneration at high frequencies. After understanding how the source degeneration network with the resistor IS and capacitor CS was connected in a single-ended amplifier, think about the differential ended image for 5 seconds. Correct. From Microelectronics 101, you know the tail current source would be in the middle of the differential topology, and each half circuit would have the source degeneration network. So the image of the type 1 source degenerated CTLE in differential should be straightforward to you. But do you see any headroom issue if the supply voltage is decreased? Think about the IR drop image at the DC bias for 5 seconds. Right, as you can see, the DC current of the current source will flow into the IS, and the IR drop of the IS divided by 2 times IS in addition to the required overdrive voltage of the current source. Therefore, the minimum input common mode voltage of type 1 source degenerated CTLE should be increased. Unfortunately, multi-stage CTLE must DC couple directly to reduce the design complexity and area overhead without any AC couple requirement. Then, the previous stage output common mode voltage would be the limiting factor if the supply voltage drops. This would explain why in the advanced process node, along with the decreased supply voltage, the type 1 source degenerated CTLE is not so popular. Do we have type 2 CTLE? Yes. Think about the image of the splitting DC current for 5 seconds. Yes, we have another choice of splitting the tail current source in each half circuit as a pseudo differential topology. We then connect the source degenerated network between each half circuit to keep the high pass frequency response as before. But do you see any subtle image of what most pseudo differential would have? Bingo! Since the current source is splitting into each half circuit without keeping the common one anymore, any mismatch between both current source would degrade the common mode rejection, such as common mode noise, supply rejection, input DC offset, common mode to differential mode conversion, etc. Also, due to the supply limitation in advanced node, the overdrive of the current source would be small and worsen the mismatch issue. So, again, I'm not saying this mismatch issue cannot be mitigated, but we must pay much attention to the mismatch variation in several performance evaluations we mentioned, no matter type 1 or type 2. Thanks to the source degeneration resistor, the source degenerated CTLE has a better linearity and maximum frequency response than the shunt-peaking CTLE. Also, the area overhead at the source degeneration network is not that significant, and the corresponding IS and CS also provide us with a more flexible pole zero response tuning and less design capacity than the shunt-peaking CTLE. Does that mean the shunt-peaking inductor is useless? Think about the bandwidth images for 5 seconds. Of course not, and the inductor does still help a lot if the area was not a concern. Let's review the source degeneration CTLE topology one more time. As you can see, the RD1 is the resistor rho, and the CP will be the parasitic associated with the device capacitance. The CS, RS of the input differential pair M1, M2 sets the pole and zero of the frequency response. Before driving into the equation, let's intuitively look at the frequency response at the DC and very low frequency. Then CS is open and parallel RC network is dominated by the RS, so the DC gain drops. On the other hand, at high frequency, the RS impedance is much bigger than the 1 over omega CS, so the parallel RC network is dominated by the CS and the gain is higher to achieve the high pass characteristic. You can try to derive the first order equation of loss pole and zero, DC gain and maximum gain around the next rate without considering the RO of loss transistor, and then do a ballpark design exercise numerically. Of course, due to the output pole, omega P2 is dominated by the RD CP and the bandwidth is limited if the CP was too much to make sure the omega P was greater than omega P1. Then both the maximum gain and the peaking frequency would be reduced. Think about the bandwidth enhancement images for 5 seconds. Right, we still can add the shunt-peaking inductor as a way of broadening the RC bandwidth between the cascaded stage such that we can make sure the peaking frequency could be at least equal or slightly greater than the next rate frequency. Again, the output pole omega P2 is translated to the complex poles by the inductor, which should be designed greater than the pole omega P1 of the source degeneration CTLE. So while people design the CTLE above 50 gigabit per second or 100 gigabit per second, the source degeneration with shunt-peaking CTLE is becoming more popular. Here is a summarized image of why we need a shunt-peaking or source degenerated type active CTLE. To provide a voltage gain, we often use the CML amplifier owing to its simplicity and robustness to convert the CML's low-pass frequency response to a high-pass frequency response as a channel equalizer. We could implement the high-pass characteristic either through a transconductance GM or an output load ZL, since the voltage gain equals the GM times ZL. The high-pass passive element as an output load is the inductor, which has a low impedance at the low frequencies and high impedance at the high frequencies. Even though people can tolerate the inductor's area overhead, the tunable inductance is quite a challenge, such that we could not adjust the equalizer high-pass response flexibly to accommodate different lossy channel profile in any link. Fortunately, adding a source degeneration network of RS and CS at the source of the differential pair devices will realize a low GM at low frequencies and high GM at the high frequencies. In order to take the common mode rejection benefits of the differential topology, the current source must be put in the central tail of the differential pair, but the tail current flowing through the RS will add more IR drop and will have a big head loop issue at a low supply in an advanced process node. Therefore, people rarely use Type 1 source degeneration CTLE recently and move to a Type 2 source degeneration CTLE, which split the current source into each half circuit without adding any IR drop. Unfortunately, this Type 2 or pseudo differential CTLE and the big eyes will suffer from common mode immunity, such as the common mode noise, supply rejection, input DC offset, common mode to differential mode conversion, etc. And we need to pay more attention in the design. Lastly, for very high speed SerDes up to 50 gigabit per second or 100 gigabit per second in the most advanced process node, the output bandwidth of each CTLE is limited by the output parasitic with the device capacitance. Therefore, people will still add the shunt-peaking inductor at the Type 2 source degeneration CTLE to make sure the second pole will be greater than the first pole of the source degeneration, such that the peaking gain and peaking frequency can be high enough. Again, the shunt-peaking inductor is only for bandwidth enhancement, and the source degeneration CTLE mainly provides the flexible pole and zero response tuning for different lossy channel profiles with better linearity and maximum flat frequency response than the standalone shunt-peaking CTLE. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and place your comments down below. Lastly, please share the video link with people who may be benefiting from it.